In this video, we are going to start studying the issue of garbage collection in concurrent programming. So in the previous lectures on concurrent data structures, I already said that in concurrency, we need to take into account the possibility of concurrent threads in collecting garbages or collecting no more used memory locations. So in this lecture and from now on, I'm going to focus on this particular problem of memory reclamation in concurrency and propose a few representative algorithms for garbage collection in concurrency. So the most of the slides are prepared by your TA in Taiwan, and so he shared the slides with me, and that's the reason why I could use these slides in this video lecture. Okay, now first things first. First things first. So let me start with the concurrent data structures in general. So this is a linked list. So you already know well about this linked list, and there's a head pointer, and the head pointer is pointing to the first node, and the first node is pointing to the second node, and on and on and on. So as we already discussed pretty extensively, the benefit of this concurrency in data structures is that multiple threads can act on the same data structure at the same time, and as a result, the performance can be optimized. And furthermore, it is non-blocking in the sense that even though the other threads are working on the same data structure, I can finish my operation if my operation and the others' operations are not conflicting with each other. So in that sense, this is a non-blocking. So I can finish my operation even though the other threads are concurrently working on the same data structure. Okay, this is the benefit. So here's an example. The T1 and T2 are the two threads, and they are executing the remove operation for the same linked list. It can be done in parallel because they are modifying the different part of the data structure, and as a result, their modification is not conflicting with each other. So far so good. And let's say that T1 removes the value 0 by updating the head pointer from the first node to the second node. And similarly, the T2 is effectively removing 20 by updating the next pointer of this 10 to the later one. Here, the null pointer in this example. Okay, and after unlinking the nodes 0 and 20, or after detaching the nodes 0 and 20 from the linked list, we want to finally deallocate the memory location because it is no longer inside data structure. So we eventually need to reclaim the memory. Otherwise, the memory consumption will spike high, resulting in some very bad system behaviors. Okay, so we want to actually call the free function for these allocations. However, the problem is that we cannot free the blocks immediately. So we already dealt with the data structures, and it already has a significant complication over sequential data structures. And this existence of garbage collection or the requirement of this garbage collection is adding much more complexity to the already complex design of concurrent data structure because of this reason. So if the nodes 0 and node 20 are immediately deallocated, then there's a problem. The reason is that maybe the concurrent threads may access the node 0 and may access the node 20 at the same time concurrently. And because of the possible existence of those threads that access the same node, the nodes 0 and 20 must not be deallocated immediately. So let me explain it in a more detailed example here. So okay, suppose that the block B is going to be removed from the data structure. But for now, let's assume that T1 is concurrently accessing the same node B, and it has a reference to, or it has a pointer to the first node that contains the value 0. And then this node 0, this T1 is going to sleep because of various reasons. For example, it wants to do some I/O, or maybe the OS scheduler doesn't like to give a slot for this T1. Anyway, T1 is sleeping now, and at the same time, assume that T2 has just removed the node 0 by updating the head pointer from 0 to 10. Okay, so if we remove and then immediately free the block, then the block B has been freed, and as a result, T1 may wake up and then access the freed block. And as a result, it is causing a use after free bug. So use after free bug is a very bad thing. The programmer should not invoke and should not incur use after free. Otherwise, if there is a use after free in the program, the semantics of the program is undefined, and as a result, the computer can do anything it wants. So that is a very bad thing. So we have to avoid this. The moral of the story is that if T2 is freeing the block right after it is removed, maybe the removed block have been referenced by the another thread, and the another thread may invoke a use after free. Okay, so in order to prevent such a bad thing, in order to prevent such a use after free error, we need to do two things. So we need to somehow synchronize multiple threads in such a way that they do not incur use after free, even for those blocks that has been detached from the linked list or other data structures. And in order to design such an algorithm, we usually focus on two aspects. The first aspect of the algorithm is this. Q1. How do I protect B from being freed? So from T1's perspective, T1 wants to access the block B after waking up. So the sleeping may not be caused on its own. Maybe it is preempted. So it doesn't know whether it is going to be asleep or not. But T1, no, what is definitely true is that T1, regardless of whether it is cooperatively or preemptively sleeping, T1 later wants to access B. That is the fact that doesn't vary. So we need to somehow say that, T1, from T1's perspective, we want to say that, I want to access this B at some later time. So please do not deallocate the block B without me being noticed. So that is basically the Q1. How do I protect B from being freed? I need to protect B from being freed, and the question is how to do that. And the other aspect of this algorithm is the T2's perspective. Here the Q2 says that when is it safe to free B? Okay, so far so good. Let's say that many other threads say that if some thread says, I'm going to access the block B, then it should not be the case that this T2 is freeing the memory block. But then how to determine whether all the threads finished accessing the block B, only after all the threads finishes accessing the block B, T2 may safely free the block. So T2 is very interested in knowing when is it safe to free the block B. So this is it is always safe to free the block B if no one is concurrently accessing the block B, and it is true if all the other threads finished accessing the block B. So we need to somehow figure out when all the other threads finished accessing the block B for answering this Q2 question for thread 2. Okay, so the answers to such questions, Q1 and Q2, how to protect the blocks and how to safely free the block, and answer to those two questions are usually called the safe memory reclamation algorithms. So here, even though this word, the three word phrases, it doesn't contain the word concurrency, usually the safe memory reclamation problem is connotated with concurrency, because in sequential program it is usually called memory leak or memory use after free bug, but this safe memory reclamation is much more difficult and much more interesting in concurrent setting. So that's the reason why when you're saying, oh, I'm working on some safe memory reclamation algorithm, it is usually meaning that, oh, I am working on concurrent garbage collection. Okay, so far so good. So we need to answer those two questions: how to protect and how to know when it is safe. Okay, so there are a bunch of algorithms that has been proposed so far, and so this problem has been known for decades, multiple decades, and the formal papers about the algorithms about this SMR has appeared since 1990s, early 1990s, and it has been already 30 years or more in the academic literature, and in the industrial literature it dates back to much earlier. For example, even in 1960s or 70s, people already know, oh, there will be a problem in concurrent garbage collection. And okay, so there are many solutions proposed so far, and we can roughly classify those into two categories. The first category is what is called hazard pointers, and the other category is usually called epoch-based memory reclamations. And actually, many proposals that has been proposed after hazard pointers and epoch-based reclamations are a combination or hybrid or variations of the two schemes. So these two, hazard pointers and epoch-based reclamations, are usually the most important algorithms we should learn in this concurrency course. Okay, and now I'm going to focus on the two algorithms a little bit more. So I'm going to tell you a little bit about hazard pointers and then epoch-based reclamations in this class. Okay, the first algorithm is hazard pointers, and let me explain how to somehow synchronize multiple threads for concurrent garbage collection by answering the question 1 and question 2 I introduced just before, and this is the hazard pointers answer. So how do I protect B from being freed? So in order for example, thread 1 to protect the block B from being freed, then hazard pointers do a very simple thing. It just writes down the block B in its own list of protected list. So the API for that is what is called the protect function. So you, at the beginning of an operation or just before accessing a pointer, you first need to declare that, oh, I'm going to reference this pointer, so before that, I want to protect the block. So that is basically the API of this protect B. Before dereferencing the block B, I need to protect it so that the other threads are not going to reclaim the same block concurrently. So far so good. And header pointer's answer for Q1 is calling protect B, which in turn is writing it down in its own list of protected pointers. And these protected pointers are also called headers because it is headers to reclaim those blocks. So that's the reason why this technique is called header pointers. So it is synonymous with the phrase protected pointers. And historically, it is usually called headers. So that's the reason why this algorithm is called header pointers. But actually, I prefer the name, the other name, protected pointers, because it better conveys what is actually going on in these pointers. So I hope you know the two names. I hope you know the two names, and header pointer is a historical name, and it is the standard name actually. And protect pointers is the name that conveys its meaning better. Okay, so far so good. And let's assume that all the threads has already written down the list of protected pointers that it will access or dereference. Now let's move on to the Q2. When is it safe to free a block B? So let's assume that you just remove the block B from the linked list by performing some CAIST or some other atomic operations. And now we want to somehow make sure that this block is not concurrently accessed by any threads. So in order to do so, what we do is that, we read the list of protected pointers of all the threads, and if B is not contained in any of the list, that means that the block B is no longer protected by anyone. It may be the case that no one protected it in the past, but even if some threads was accessing the same block B, then it is guaranteed that that thread has finished its operation and the block B is no longer accessed, provided that the list of the protected pointers of all the threads it is not containing the block B. If the protected pointer list contains the block B, it effectively means that the block B may be concurrently accessed by the other threads. Okay, so this is the simple answer. So that's one of the reasons why header pointer is the earliest SMR algorithm that has been proposed so far. So the answers to these two questions is very simple. You write down the protected pointers in some list, and then you read it. You read it and determine whether some block will be safe to deallocate or not. So far so good. And let's see an example here. In the header pointers, suppose that this T2, T1 is iterating over the linked list, and it just picked the block B. And it needs to protect the block B before dereferencing the block B. So if you want to traverse to the next block, you have to dereference the block B. But before that, the T1 needs to protect the same block just before dereferencing it. That's the reason why it is protected before accessing the next node. And at the same time, let's assume that T1 is just going to sleep, and T2 has been removing the node with value 0 by updating the head pointer from the node 0 to node 10. And so far so good. And recall that T1 would have already written B in its protected pointer list. And T2 is trying to deallocate the same block. And it needs to determine whether it is safe to free the block B or not. In order to know that, it just reads the protected pointer list. But in order to do so, it has to signify its intention that, oh, this block B is removed from the data structure, so we want to deallocate it. It may be possible that it is concurrently accessed by the other threads, but anyway, regardless of whether it is the case or not, we want to actually free this block at some point of time. Maybe it is not now, but later, at least later, we want to deallocate the block B. So in order to signify that intention, there is another API that is called retire, which means that B is detached from the linked list, so we want to retire it. But please do not deallocate the block immediately, because it may be possible that it can be reused later. So far so good. And yeah, retire. And you retire the block B. And now T2 or the other threads want to actually deallocate the block B. Because it is retired, it is no longer in the data structure. So we want to deallocate it. But in order to determine whether it is safe to do so, we are figuring out the list of the set of blocks that is retired, but it is not currently protected at all. So the retired but non-protected pointers, those are subject to reclamation. All the other pointers should not be reclaimed. If it is not retired, you should not reclaim it. If it is retired but it is concurrently accessed by the other threads, you should not deallocate it. So that's the criteria. Those pointers that is retired but it is no longer protected, they are subject to collection. They are safe to free those locations. And this kind of job is usually called by a collect function, which may be called by any threads. And in this collect function, we list up the retired pointers, and figure out which pointers are not protected by any threads. And those blocks will be deallocated in this collect function. So far so good. And now suppose that T1 finishes accessing the block B. For example, it already read the next pointer. And after reading the next pointer, this node, it doesn't need to read the block B again. So that's the reason why we can call a function that is named unprotect, which signifies the fact that, oh, B was a protected pointer, and we now no longer want to protect it because I finished accessing the block B. So far so good. And by as an effect, this unprotect removes B from the list of protected pointers of the same thread. So if you call the collect again, then you can safely delocate B because it is already retired, but it is no longer protected by the thread T1. T1 called unprotected B, which means that the block B is no longer necessary to that. So that's the reason why we do that. So we unprotect it, and as a result, T3 or any other threads may be able to delocate it because it is retired, but it's not protected. Okay, so as a result, T3 just has freed the block B. So far so good. And here's an example. Here is the driver stack that is in a slightly different style than one that is written in the repository, but it is actually the same algorithm. It has omitted the orderings, but except for the syntactical differences and the ordering differences, they are actually the identical with the driver stack in the repository. That is already discussed in some of the earlier videos. How do we apply header pointers in this example? So that is basically the topic of this slide. And recall that the line 16 is unsafe because it is trying to access the next node. It is trying to access the next node by dereferencing the current node, but maybe without protection, maybe this node has been reclaimed by this free function at line 18. So to protect it, we insert these 3 lines of code just before the line 16. So let's read it. I'd like to protect the block B, and then I'd like to reread the pointer that so you want to protect cur, and cur is loaded from this is head. And after protecting this current pointer, you need to make sure that that is still remaining in the main memory. So in order to do so, after protect, you read it again. This is the very pointer that has resulted in the current value. And by doing so, we are reloading it, and if it is different from the current pointer, then we just bail out. We just begin from again. So it doesn't harm because we are going to go to the beginning of the loop, ignoring all the intermediate computations. And if this condition is met, this equality holds if the memory still contains the current node's pointer, then it is the case that I'm still in the data structure, and I'm safe to protect so it was safe to protect the node cur. And after this check, the current is actually firmly protected by myself, and as a result, I can access this current. I can dereference this current node right after this 3 lines of code. And also, after finishing accessing the node, I need to signify the fact that I finished accessing the location, and that location is no longer necessary to be protected. So that's the reason why we call unprotected cur here. Cur was protected in these 3 lines of code, and cur is accessed here at line 16. And after that, we want to just signify the fact that we don't want to bother more, so we are calling unprotected cur. And the contract here is that after unprotected B, unprotected cur, you should not access cur again without the protection in play. So far so good. And finally, we need to replace this free with what is called retire. And as I explained quite extensively, you should not call the free immediately. You have to make sure that all the other threads are finished accessing the same block, and that's the reason why we need to do free. We need to do retire instead of immediately freeing it. So in effect, this retire is just writing down my intention that this cur must be deallocated at some point of time, but it may be the case that it is not now. We need to wait a few threads finish accessing the same node. Okay, so it is everything we need to do for the traverse stack. We need to protect pointers before dereferencing it, and we should not forget the unprotecting the local pointers, because if it is remaining in the program, then the locations or blocks are protected more than necessary. That will degrade the performance. Anyway, we can easily transform a traverse stack into a header pointer protected traverse stack by inserting these three aspects. But you can see that this API is a little bit error prone. The reason is that you need to make sure that what is currently dereferenced is actually protected before, and you want to somehow make sure that is satisfied without And furthermore, you need to validate the fact that the pointer cur is still there. It is a little bit unintuitive, and so it is actually a requirement of the hazard pointers, but it is often forgotten by the users. So there are some approaches to mitigate the problems of those two. The first problem is that we may forget the protection, and the second problem is that we may forget the validation of the pointers in the header pointers. And the Rust programming language can be used to mitigate such problems by designing a better API. For example, we can make an API of pointers in such a way that without protection, you cannot dereference it. It is mandated by the Rust programming language. We can design it in such a way. And furthermore, you need to act the reference current only after the validation. And this idea of validation may also be incorporated, expressed on top of the Rust type checker. That's the reason why we can design a safer API inside Rust that automatically satisfies that helps automatically satisfy some of the requirement of the header pointers. But still, there are a few more things to do, a few things that the Rust compiler cannot automatically reason about. And in such cases, we need to somehow manually reason about this usage of header pointers. Furthermore, header pointers has more drawbacks. And the first drawback is that it is actually not very fast. The reason is that it needs to issue a very expensive fence for each iteration of data structures. So for example, in linked list, if you want to traverse to, for example, the faraway node, then you need to somehow follow the nodes from the head pointer to the target. And the problem is that header pointers insert a very expensive fence for each iteration. So the synchronization, so the fence is used in order to synchronize with the collect function. So recall that collect function needs to read the set of protected pointers in order to make sure that the pointers it will free right after is actually not protected by any threats. And in order to do so, this protect function and this collect function needs to synchronize with each other. And that synchronization is achievable only with the very expensive fence in the current hardware. That's the reason why header pointer is usually very not fast. So yeah, so this expensive fence's name is store load fence, which means that the store and later loads should be ordered. According to the program order, and you can safely think of it as sequentially consistent fence because all the fences that satisfy this property, store load fencing, is actually the biggest fence, and that is actually sequentially consistent fence in the C and C++ terminology. Okay, so let's see this animation once again. So in each iteration, it needs to issue the fence, and that's the reason why the fence should be issued for the length of the list times. So it's not very fast. So empirically, header pointers are usually assumed to be slower than the other alternatives by 3 times. So that is very bad. We can utilize only 30 or 40% of the entire bandwidth or capacity when using these header pointers. And the second problem is that actually these header pointers is not widely applicable to many data structures. So that means that there are many data structures that cannot be implemented with header pointers. And let me explain why. So the one of the representative example of that is what is called a change retirement. And in this example, so T1 is protecting the first block, and let's assume that T2 has been removing the first and the second block at the same time by performing cuts on the head pointer from the original head pointer to the block 2, B2. If that suppose that happens, and let's see what will happen. And this T2 is going to protect the 2 node, B0 and B1. They can be retired. The reason is that they are no longer approachable from the linked list, and because they are just unlinked or detached from the data structure. So we can safely retire those B0 and B1, or at least we imagine that we should easily retire this B0 and B1. Okay, so far so good. And now suppose that we invoke the collect function, and recall that this collect function actually frees the memory blocks that has been retired, but it is not protected at all. And surprisingly, B1 satisfies this criteria because it is retired as a part of the change retirement. But it is not protected yet because T1 only protects the block B0, And B1 is beyond the imagination or beyond the reach of the T1, because the T1 is currently accessing B0 and it doesn't know anything about B1. So it is so that's the reason why B1 is retired but is not protected, and as a result it can be reclaimed in a concurrent clock function. Suppose that B1 is freed now, because there is a collect function that invokes such changes. But now the problem is that T1 protected B0 and it wants to traverse to the next node, and T1 will access B1 and dereference the contents of B1. But it is going to be used at the free because B1 has already been freed by T2 before T1 advances to the next node. So the moral of the story is that, B1 is very strange. It is in the algorithm of hazard pointers. We need to be able to deallocate the blocks. But however, actually deallocating it may incur a lot of problems because maybe there are concurrent threads that is accessing B0 that will traverse to B1 without asking the other threads. So it is a problem, and that's the reason why this example is not supported by hazard pointers. And this example that I call a chain retirement, it is happening many times in the real-world concurrent data structures. So as a result, hazard pointers applicability is significantly limited, and it can be applied to a few simple algorithms only. And if multiple locations are modified at the same time, multiple nodes are changed, for example, removed from the data structure at the same time, we cannot use the hazard pointers technique. Okay, so far so good. And so in the next video, we are going to resume from the next algorithm, the epoch-based reclamation algorithm, or shortly EBR. And this EBR solves the three problems of hazard pointers. It is easy to use, and it is much faster than hazard pointers, and it is much more widely applicable than hazard pointers. And it fixes all the problems of hazard pointers, but by sacrificing some of the most important criteria for this SMR. So in the next video, we are going to study this EBR and discusses the pros and cons of the hazard pointers and epoch-based reclamations, and somehow discuss compare those two in a qualitative way.